Hi friends, welcome back to our YouTube channel. Today we have to discuss about IEEE 754 floating point representation using single precision format in computer architecture course, computer organization course, computer organization and architecture course. In the previous videos, we are already solved three different example problems on the floating point representation. Now, in this video, we have to discuss about different example problem, that is represent minus 29.5 with the base 10 in IEEE 754 single precision format using implicit normalization. Previous three problems on only positive floating point numbers. Now this problem is negative floating point number. How a negative floating point number can be represented in IEEE 754 single precision format. Before solving this problem, first of all, you have to know about IEEE 754 single precision format. It contains 32 bits. That 32 bits are starting with 0 and ending with 31. Total 32 bits. That 32 bits can be divided into three fields. The first field can be called as mantissa. So 23 bits are allocated for mantissa, starting with 0 and ending with 22. The second field can be called as exponent. That can be denoted by capital E. 8 bits are allocated for exponent, starting with 23 and ending with 30. Here mantissa can be denoted by capital M. Next, last one bit is allocated for sign bit. So 30 to 31. Only one bit can be allocated for sign bit. By using that sign bit, we have to know that whether we have to represent a positive floating point number or a negative floating point number. Suppose S value is equal to 0, it represents a positive floating point number. If S value is equal to 1, it represents a negative floating point number. Okay, next one. Here we have to use two types of normalizations. First one is explicit normalization. Second one is implicit normalization. Among the two normalizations, the default one is implicit normalization. Okay, the definitions can be discussed in the previous videos. The formula for explicit normalization is -1 whole power s into 0.m into 2 power e minus bias. Here S is nothing but sign bit, M is nothing but mantissa, E is nothing but biased exponent. Here bias value is 127 in the case of single precision format. Whereas in the case of implicit normalization, the formula is -1 whole power s into 1.m into 2 power e minus bias. In both normalizations, bias value is equal to 127. How we are getting bias value is equal to 127? The formula for bias is 2 power n minus 1 minus 1, where n is nothing but number of bits allocated for exponent. How many bits are allocated for exponent? 8 bits. So that 2 power 8 minus 1 minus 1, that is 2 power 7 minus 1, that is 127. This is the bias value. So among that two normalizations, the default one is implicit normalization. Whether they are given in the problem or not, you have to use the default normalization is implicit normalization. With these basic details, we can go to the problem. So here the given decimal number is minus 29.5. Okay, here the given decimal number is a negative number because minus sign is there in front of the 29.5, so that we can say that the given decimal number is a negative floating point number. So by observing this, we have to know the sign bit value. Okay, so here first we have to write the sign bit value. Here sign bit value is equal to S is equal to 0. To represent the positive floating point number, we have to use the sign bit value is equal to 0. To represent the negative floating point number, we have to use the sign bit value 1. Here minus 29.5 is a negative floating point number, so that we can say that sign bit value S is equal to 1, because given decimal number is a negative floating point number. Negative decimal floating point number. Okay, so that we have to know the sign bit value. Yes. Next, you have to know the mantissa value M. To know the mantissa value, you have to convert the given decimal number into binary form. Okay. So minus 29.5. Okay. So here it contains integer part and it contains fractional part. So here integer part is 29 and fractional part is 0.5. So each one is separately converted into equivalent binary number. So integer part can be converted into equivalent binary number by successively dividing the given number until the quotient value is equal to 0. Once we are getting the quotient value is 0, you have to write the reminders from bottom to top. So here 29 can be successively divided with 2, 2 14s, 28, remainder 1. Now quotient value not equal to 0. Now again we have successfully divided with 14 with 2, 2 7s, 14, remainder value 0. So quotient value not equal to 0, so that successively divided with 2, 2 3s, 6, remainder 1. Quotient value not equal to 0, we have to successively divided with 2, 2 1s, 2, remainder value 1. So quotient value not equal to 0, it is successfully divided with 0, 2, 2 zeros, 0, remainder 1. Now quotient value we are getting as 0, so that we have to stop the dividing the given number with 2. Now you have to write the remainders from bottom to top. Only remainders you have to write. So 29 base 10. So binary form is 1 1 1 0 1 base 2. This is the binary equivalent of 29. Next, you have to take the fractional part. To convert the fractional part, you have to successively multiply with 2, and whatever the value we are getting from that one, you have to separate the integer part. Only by taking the fractional part, that can be multiplied with 2 until we are getting the 0 value. So now the fractional part is 0.5. It is multiplied with 2. So then we are getting 1.0. So here the integer part is 1. You have to separate the integer part, and the remaining part is fractional part. Fractional part contains only zeros. Whenever the fractional part contains only 0, you have to stop the multiplying with 2. So then write the separated integer part from bottom to top, so that we are getting 0.5 base 10 is equal to only fractional part we are getting, so 0.1, only this single one is there. So this is base 2. So integer part binary equivalent is there, fractional part binary equivalent is there. So therefore 29.5 base 10, the binary equivalent is, integer part binary equivalent is 111 0.1, point fractional part binary equivalent is 0.1. So this is 0.1 base 2. This is the binary equivalent of 29.5. Here we do not mention minus, because already minus is by using the sign bit we have to put s value is equal to 1. So up to that point, so minus sign is completed. Now I am taking 29.5 that can be converted into binary equivalent. Now 1101.1. Okay, so this is the binary equivalent we are getting. Now this binary equivalent can be converted into implicit normalization form. In the given problem, use only implicit normalization. So here in the implicit normalization, you have to write this binary equivalent in the form of 1.m. M is nothing but 97. 97 is nothing but fractional part. Okay, so here to get 1 point something, we have to move the decimal point towards left. At a time, 1 bit can be moved. Okay, so first this decimal point can be moved to this one. Next, this decimal point can be moved to this one. This decimal point can be moved to this one. This decimal point can be moved to this one. So 4 positions we have to move from right to left. Okay, so then what we are getting? So here 1.11011. This is we are getting. So move the decimal point 4 positions towards left from right to left. So 4 positions we have to move, so that you have to write 2 power 4. Each time decimal point can be moved from right to left, we have to use 2 power 1 one time. Next another time 2 power 2. Next another time 2 power 3. Next another time 2 power 4. This decimal point can be moved to this place. It can be multiplied with 2 power 1. This decimal point can be moved to this place. It can be multiplied with 2 power 2. This decimal point can be moved to this place. So it can be multiplied with 2 power 3. This decimal point can be moved to this place. It can be multiplied with 2 power 4. So finally we are getting 1.11011. 11011 into 2 power 4. So it is in the form of 1 point m into 2 power e minus bias value. So this is the implicit normalization formula. Okay. Now, what is the m value? By comparing this formula with this one, so we are getting what is the m value? M is equal to, m is nothing but after the decimal point, whatever the value is there, that value can be treated as mantissa. So this part can be treated as mantissa. It is always a fraction value. So 0.11011. This is the mantissa. 0.11011. This is the mantissa. We already know the S value. We already know the mantissa value. Next, you have to know we have to find out the E value. Okay. Third one, E value. So here, when we are comparing this formula with this one, we get the M value. Next one, 2 power E minus bias is equal to, it is equivalent to 2 power 4. And we are comparing with this one with this one. So here bases are equal, then powers are also equal. E minus bias is equal to 4. Then what is E value? E value is equal to 4 plus bias. What is the bias value? We already know the bias value, that is 127. So 4 plus 127, that is equal to 131. What is the binary equivalent of 131? Here we have to use the 131 can be written in the form of nearest to 2 powers. So that is 128 plus 2 plus 1. Okay, 128 is 2 power 7. 2 is nothing but 2 power 1. 1 is nothing but 2 power 0. Okay, so whatever the 2 powers are there at that places, you have to put 1. Whatever the missing 2 powers are there, you have to put zeros. Okay, so here first, starting with 2 power 7, it is already existed, so that its value is 1. 2 power 6, it is missed, so that its value is 0. 2 power 5, it is missed, so that its value is 0. 2 power 4, it is missed, so that its value is 0. 2 power 2, it is missed, its value is 0. 2 power 1, yes, it is existed, so that its value is 1. 2 power 0, it is already there, so that its value is 1. Okay, so here you have to write in this way: 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. So what are the 2 powers are there? 2 power 7 is there, 2 power 1 is there, 2 power 0 is there. Remaining values are filled with zeros. So this is the value you are getting. Okay, this is the simple procedure. Next one. So we are getting E value also. Once you are knowing the S value, M value and E value, you have to substitute in the 32-bit format. So that is, this is mantissa part. It contains 23 bits. This is biased exponent. It contains 8 bits. This is sign bit. It contains 1 bit. Okay. What is the S value? S value is 1. Because it is a negative floating point number, so that S value put it as 1. What is the exponent value? Exponent value is 8 bit. 1, 4 zeros, 1, 1. 2 power 7, 2 power 6, 2 power 5, 2 power 4, 2 power 3, one more 0 is there. Okay. 8 bits are there. Okay. Next one, what is the mantissa value? Mantissa value is this one. You have to write only after the decimal point, whatever the number is there, that number can be written. Okay. There is no need of including 0 because mantissa is always a fraction number. So 1, 1, 0, 1, 1. 1, 1, 0, 1, 1. How many bits are there? 5 bits are there. How many bits are allocated for mantissa? 23 bits. So 23 bits, only 5 bits are there. Remaining 18 bits are filled with zeros. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So in this way, we have to represent minus 29.5 in IEEE 754 single precision format. So here 1, 5 zeros, double 1. Okay, total 8 bits you have to write here. Any bit is missing, so the binary conversion is wrong. You have to check it, no problem at all. Okay. So I hope all of you understanding this video. If you have any doubts, please put your doubts in the comment section. I will try to clarify your doubts. If you really understanding this video, please click on the like button and share this video to your friends and classmates. If you really like this video, please subscribe my YouTube channel, Divvela for getting future updates in my YouTube channel. Forward this channel to your friends and classmates. It is really helpful, and told them please subscribe my YouTube channel. Thank you. Thank you one and all for watching this video. In the next video, we can go for double precision floating point representation.